Okay, if we are given two three-dimensional vectors, say vector A with components ax, ay, and az, and vector B with components bx, by, and bz, then we define their scalar product A dot B as the sum of the products of their corresponding components. In other words, A dot B equals the product of the corresponding x components of the vectors A and B, ax times bx plus ay times by plus az times bz. This is called scalar product since, as you see, the result is a scalar, a real number. There are alternative names of this scalar product. One is the dot product, since we have dot between the vectors, and also another common name is the inner product. After this simple definition, we are ready to find a relationship between the magnitude of a vector and the scalar product. If you remember the definition for the magnitude of a vector in 3 dimensions, it is calculated by the Pythagorean theorem as A equals square root of ax squared plus ay squared plus az squared. And remembering the scalar multiplication of two vectors, A dot B, we substitute B equals A into this equation and the corresponding formula for the scalar product. That is, we say that the magnitude of vector A is just the square root of the scalar product A dot A. And it is shown by this formula as the magnitude of A equals square root of the scalar product of A with itself, that is A dot A. Or, if you like, since both sides are scalars, that is numbers, then we can take their square as A square equals A dot A. Then we purely obtain A dot A in the right hand side. Alright, everything is so far so good. Then, what about the standard basis vectors in 3 dimensions? That is, I, j, and k. The answer is in the next page. Remember that I, j, and k are unit vectors. In other words, magnitude of each one is 1. So, it is a very easy task to show that I dot I equals 1, j dot j equals 1, and also k dot k equals 1. Besides, we can easily show that scalar product of any standard basis vector, say I, with another standard basis vector, say j or k, we obtain 0. Let me solve one of them. Vector I can be represented as 1, 0, 0, corresponding to the x, y, and z axis. And also j is 0, 1, 0, corresponding to the x, y, and z axis. As a result, their scalar product is obtained as 1 times 0 plus 0 times 1 plus 0 times 0. That is 0. In conclusion, we can write that I dot j, j dot I dot k, k dot I, j dot k, and also k dot j equals 0. Due to the fact that scalar product of two vectors is nothing but a number, then a dot b is equal to b dot a. The definition of scalar product of two vectors allows us to claim that scalar product is distributive over vector sum. That is, a dot b plus c equals a dot b plus a dot c. Because b plus c is another vector, using the commutative property of scalar product of two vectors, we can also write that a dot b plus c equals b plus c dot a. That is, the order of scalar product is not important. We said that scalar product of two vectors is just a number. Then number times number is just a number. Then for any scalar c times the scalar product of two vectors a dot b is equal to a dot b times c by changing the order of multiplication, we can easily show that the result is the same as the scalar product of c times a dot b and also a dot c times b. So, for a more sophisticated discussion of the scalar product of two vectors, we will introduce the renowned Cosine Law. For the triangle in this figure, if we denote the three angles as A, B, and C, the cosine law for this triangle can be written as A square equals B square plus C square minus 2 times B times C times cosine A. That is the angle between the edges B and C. And it is not difficult to see that these two equations also hold. With this in mind, we can now concentrate on the notion of subtraction of two vectors to go one step further in scalar product of two vectors. Making use of the cosine law we previously defined, we can now show that A dot B equals the magnitude of A times the magnitude of B times the cosine theta, where the theta is the angle between the positive directions of A and B. Now we will prove this formula in the next slide. Remember that subtraction of two vectors A and B, that is A minus B, is obtained by the tail-to-tail fashion. So, this is a triangle, then there is a relationship among the magnitudes of the vectors A, B, A minus B, and this angle between A and B. Square root of the magnitude of the subtraction A minus B is equal to the sum of the square root of the magnitudes of A and B minus 2 times A times B times cosine of angle theta. Here, since A minus B is a vector, then the scalar product of any vector with itself is equal to the square root of the magnitude of that vector. Then we are free to write that this is equal to A minus B dot A minus B. For the reason that scalar product is distributive over vector summation, we obtain that A dot A minus A dot B, again minus B dot A plus B dot B. We have previously said that scalar product of two vectors is commutative. Then B dot A is replaced by A dot B. Then the result becomes A square minus 2 times A dot B plus B square. Here, please pause the video and go back to your lecture notes in this web page and correct this minus as plus. Anyway, you see A square and B square appear in both sides of this equation. Therefore, they are cancelled. So, we get minus 2 AB cosine theta in the left hand side and minus 2 A dot B in the right hand side. Here, minus 2's are cancelled, and finally we proved the formula for A dot B, which is claimed in the previous page. Right, so far I've talked about the mathematical formalism of the scalar product of two vectors. The next thing I would like to talk about is the relation between the scalar product of two vectors and the projection of any vector onto another. Consider two vectors A and B like in this figure. Another type of product of two vectors is the vector product. By definition, it satisfies the following three conditions. Condition 1 states that the vector product of two vectors A and B, written as A cross B, results in the unique vector whose magnitude is A cross B equals AB sine theta. Here, theta is the smaller of the two angles between A and B. It is acute angle. The two other common names for the vector product are the cross product because of the symbol cross in its notation, and the outer product. Okay, that's enough for condition 1, and let's discuss condition 2. The vector A cross B is perpendicular to the plane spanned by A and B. This means that A dot A cross B or B dot A cross B equals 0. And comes condition 3. The direction of A cross B is determined according to the right-hand rule, as we discussed earlier. Here, slide vector A and vector B parallel to themselves so that they touch tail to tail, like in the case of subtraction of two vectors. Then draw an imaginary perpendicular line to the point where their tails meet. Now, imagine that you grasp this line with your right hand and sweep your fingers from A to B through the smaller angle between them, that is theta, your upright thumb shows the direction of A cross B. In other words, A, B, and A cross B form a right-handed triad. Then, this brings us to the end of conditions. Next, we will discuss the cases where the angle theta between them varies. It directly follows from the equation, that is, magnitude of A cross B equals AB sine theta, that if two vectors A and B are parallel, that is, theta is 0, then vector product of these vectors is the null vector. So, A cross B is 0. Then we write A cross B is 0 if vector A is parallel to vector B. For the case in which two vectors are perpendicular, that is, the angle between them is 90 degrees, we have for the magnitude of their product that A cross B equals A times B, since sine of 90 degrees is equal to 1. We mathematically show this as magnitude of A cross B equals A times B if vector A perpendicular to vector B. So, we have looked at the definition of the vector product of two vectors and some cases where the angle between them varies. Then, let's move on to some additional properties of them. Unlike the scalar product of two vectors, the first important property of the vector product is that it is anticommutative, which is seen from the geometric consideration in this figure. This means that you must pay attention to the order of vectors in a vector product. Indeed, A cross B and B cross A are antiparallel to each other, as shown in this figure. Consider the so-called triple cross product, A cross B cross C. We claim that the vector product is not associative with respect to the vector product. That is, A cross B cross C is not equal to A cross B cross C. However, the vector product is associated with respect to the multiplication of a constant C. That is, C times A cross B is equal to C times A cross B or A cross C times B. Furthermore, the vector product is distributive over vector summation. It is A cross B plus C equals A cross B plus A cross C. Similarly, A plus B cross C is equal to A cross C plus B cross C. These results can easily be verified by geometrical consideration and also by some algebraic manipulations. So these are the basic properties of the vector product of two vectors, and this is time to discuss an application of the vector product. From the definition, the magnitude of A cross B is equal to A times B times sine theta, we see that this magnitude is equal to twice the area of this triangle whose coterminous sides are by the vectors A and B. Equals saying the magnitude of A cross B is equal to the area of the parallelogram spanned by vectors A and B. So that brings us to some conclusions about the vector product of two vectors. It immediately follows from condition 1 that the vector product of any two parallel vectors is 0. This leads to the conclusion that the vector product of a vector with itself is the null vector. Now we can write this conclusion for the standard basis vectors as I cross I, J cross J, and K cross K equal to null vector. Another set of identities for standard basis vectors follows from condition 3 that I cross J equals K, J cross K equals I, K cross I equals J, J cross I equals minus K, K cross J equals minus I cross K equals minus J. Notice that these two equation sets automatically satisfy condition 2. In the next slide, we suggest a method to remember these equations without pain. In order to remember easily the two preceding equation sets, there is a good mnemonic in terms of cyclic arrangement. First, write that I, J, K, again I, J, K. Then the vector product of a vector, say I, with its right neighbor J is the next following vector, K, when reading to the right. The vector product of a vector, say I, with its left neighbor, it is K, is the next following vector minus J when reading to the left. Now, using these mnemonics, we will find the components of the vector A cross B. The components of the vector product A cross B are deduced by using the two equation sets as we have previously derived, such that the x component of the vector product A cross B is equal to AY BZ minus AZ BY. And the y component of A cross B is equal to AZ BX minus AX BZ. And finally, the z component of A cross B is equal to AX BY minus AY BX. And using the unit vector notation, you can construct A cross B as this equation. This seemingly awkward equation is asymmetric, and this makes it hard to remember. If we have a closer look at this equation and recall the evaluation of a 3×3 square matrix, we realize that the vector product A cross B with its components can easily be deduced from this determinant. That is, A cross B is equal to I times the determinant of this part minus J times the determinant of this part plus K times the determinant of this part. Now, again, we suggest a method to remember this result. A mnemonic to evaluate a 3×3 determinant in an easier manner is presented in this figure. First, Extend the matrix by repeating the first two columns to the right of the third column. The value of the determinant is the sum of the products corresponding to the three complete right diagonals. It is A, E, I plus D, H, C plus G, B, F minus the sum of the products corresponding to the complete left diagonals. That is minus G, E, C minus A, H, F minus D, B, I. With the help of this mnemonic, it is no longer hard to deal with equations involving vector products. For instance, the following properties of the vector product, which we stated before, can now easily be verified, such that A dot A cross B equals B dot A cross B equals null vector, which means that A and B are perpendicular to the plane spanned by A and B. And we have A cross B equals minus B cross A. It is anticommutative property of vector product. And C times A cross B equals C times A cross B equals A cross C times B. And A cross B plus C equals A cross B plus A cross C. It is the distributive property of vector product, equals saying A plus B cross C equals A cross C plus B cross C, and also A cross A equals zero vector, which means that the vector product of two parallel vectors is nothing but the null vector. So, this is the end of chapter 3, that is vectors. See you in the next chapter.